anybody notice what the adjustment is?
Oh,
wow.
Number 7 together.
Dang. You guys were really paying attention yesterday, I guess.
We stated
That we need to take a closer look at it, yeah. The big change is right here, alkenes versus alkynes. I had alkenes ranked higher. We're going to look at a problem that's going to address what's going on with this issue between our alkenes and alkynes. We run into this weird numbering issue, and we also run into an alphabetical issue when going through and trying to name them if they both show up in the same compound. Okay? So we'll address that issue when we see it, which I'm pretty sure is the next slide here. One thing I do want to address back with the sapling homework, a lot of people are going through and starting and noticing that that first assignment has a lot of nomenclature in it, and that's because typically I go through and delete questions, and I didn't get a chance to go through and delete them. With the nomenclature questions as well, people are noticing that you have to provide the full name. The issue with sapling and full names, if you make one simple mistake, the whole answer goes wrong. You put a space in the wrong place, wrong. Dash in the wrong place, wrong. Okay? So it can be very difficult and frustrating to go through and answer those questions, which is why typically you only see one example of it in the homework. But since I haven't had time to go through and delete them, you have a lot more than that. I would recommend testing one question at a time first, see what you can do with it, and then just move on to the next problem type, which may require you to click down through a couple different problem sets. Okay? If you're really good at nomenclature, remember I did say 30% counted as full credit for the homework, and you're awesome at nomenclature, drop your 30% right there on that first part, then you can just start clicking through the rest of them. Okay? But try and do a little bit of practice with those. Realize that what you're expected to do are multiple choice naming. With that said, here you go. So we'll take a little bit of time for you guys to go through and work on these. Again, we're only doing a little bit of time because we're running out of time. If you got questions about how to start with any of these. So that first one, a lot of people seem to be questioning on that. Go through the standard rules. Don't worry about how it looks or what the name comes out as. Just follow your standard rules. So our first rule was identify the longest carbon chain. I would recommend that you circle the longest carbon chain, because that way when you go back to figure out what your substituents are, you can't double dip. Okay? Because you've now circled it and identified this is part of the longest carbon chain. It can't be a substituent. Okay? How many carbons are in that chain? 2, which gives us F. What's the functional group? We've got to be a little bit fun with the pronunciation in this case. Let's stick with triple bond. How do we name our triple bonds? With the Y-N-E. And we've got ethyne. Okay? When you see this structure float around, almost guaranteed you're not going to see that name. The name you're going to see instead, oh, fine. Let me fix it. It's trying to be all fluid.
Oh, this is way better.
You're being serious, right?
Yeah.
Okay, just checking.
Each letter has its own space.
We've got acetylene. Right?
Acetylene.
Why do we call it acetylene? Old school chemistry name. That's what it's coming down to. So it's a common name for this compound. You'll typically see it referred to as acetylene, not ethyne. Okay? You will probably show up, yeah. And there's another name that's usually associated with this, which we'll talk about hopefully today. If you remember way back when we talked about hybridization, what's the hybridization of that carbon? SP. What happens to the electronegativity of that atom as we decrease the hybridization? It becomes more electronegative, to the point that now that SP carbon, for our first approximation for our purposes, comes out to something like an oxygen, which means what about that hydrogen?
It's pulling electrons from the hydrogen.
It's taking electrons away from the hydrogen, making the hydrogen partially positive. Good answer. What would its classification be as far as our chemistry?
Acidic.
It's an acidic hydrogen, okay, which means I can go through and take the electrons entirely away, and I can generate this species. Try and be neat again. with a lone pair on that carbon and a negative charge, and then we'd have our H+.
Can't the other side do the same thing?
The other side can do the exact same thing. We'd only see it happen once. Why only once at a time?
Oh, because then it would have too much
It would
charge.
have too much charge. Okay? The name for this species, and this is the one that you'll probably see more frequently, acetylide. Okay? And what we're referring to is that negatively charged. So acetyl, well, sure, why not? Different color. The acetylide ion. What's going to be special about the acetylide ion?
It's basic.
It's Bronsted-Lowry basic, and it's a nucleophile. We now turned a carbon into a nucleophile. We haven't seen that really happen very often. There's only a few species that will do that for us, and we'll see that a lot more frequently happen in second semester organic chemistry, just because it's very difficult to generate a negatively charged carbon. Why? Why is it not stable? True, it's charged, but we can generate a negatively charged oxygen just fine.
It's not electronegative, it's not big.
It's not electronegative, it's not big, there's no resonance, okay? There's nothing to actually kind of minimize that overall negative charge. Okay? Next species. How do we name that next one? To the right, sorry, this guy.
Count all the carbons.
Find your longest carbon chain and circle it. Okay? This is a common mistake I'm seeing with this, is saying, oh, the triple bond is the highest priority. Okay, well, if the triple bond's the highest priority, let's start with it. No, connect your carbon chain all the way through. Okay, how many carbons are in our carbon chain?
8.
You guys can clearly count faster than I can. So we've got the oct. What's the functional group that we've got?
Time.
Triple bond, so we've got the YNE ending. Where's that triple bond located within that octal chain? Carbon number 4 from both sides, so we don't have to worry about which side we number from. Okay, so we end up with 4 octine. What about lower left corner?
5 chloro-1-pentyne.
Holy
That's what I got.
junk, guys. Way to just name it all out there. I can't write that fast. Longest carbon chain,
5.
so we've got a pent.
Time.
What's our functional group, our primary functional group?
Triple bond.
The triple bond is a higher priority than our halogen, so we're going to name based on the triple bond, which is the YNE ending. Okay. We will want to specify where that triple bond shows up, and this is the next then question. Which way do we number? 1, 2, 3, 4? Five.
The triple bond being the lowest number.
Triple bond being the highest priority should be the lowest number. So we will start our numbering to the far left and continue all the way through. We'll end up with our 1-pentyne, and what's our substituent?
Chloro.
A chloro, and we call it 5-chloro-1-pentyne.
So it's not okay to assume 1. If it's not said.
If you have multiple substituents, you should specify it. For sure then, if you're only one substituent, you can probably get away with leaving the 1 off. When it comes to sapling homework, you should be including the 1s pretty much all the time, and they shouldn't mark you wrong for that. Okay. With rings, it's different. With rings, we can assume that our starting position is always at 1. Okay, and that's why we typically don't include the 1 with the ring, because by definition, our highest priority is at 1. With these functional groups, it's not by definition at that 1. Okay, so we should go through and add that extra layer of information just to make sure everybody gets it correct. I'm going to erase everything just to clean it up. How about that last one?
Doesn't make sense because you have alkyne and alkene. So which one do you? I'd assume alkyne. But then I almost.
So I would argue you're actually going too far out there. First thing I want to hear is what's your longest carbon chain?
7.
Ooh, okay, never mind. Apparently you guys already knew that. So we would identify our longest carbon chain. Is it really 7? 1, 2, 3, 4, 5, 6, 7. Okay, you were right. Right again. So we have the hept. But now what?
I would call heptine.
Alkenes higher up, so therefore we would go.
So alkenes have a slightly higher priority. So we would put the alkenes in kind of an odd spot. And so this is where we're going back to that rule and deciding our priorities. The alkenes and the alkynes technically have the same priority. Okay? When we put it into the name, we'll put it into the name alphabetically. Okay? And since we're looking at an ene versus ein, which one should show up in our name first? The ene. Okay, so we can go, I'm going to need some more space on this one, so I'll shift it. Hopefully you guys can all see it.
Where do you start your numbering at?
That's what we're about to get to in the next one. So we've got our ene is going to show up first. We'll drop the e off the end of it. Okay, so we'll go ene, and we'll finish it with our ein. You'll notice that I left some spaces in there. What are those spaces for? The numbers on where to actually put each of those positions. Okay, and this is where we can run into an issue with not really priority, but dealing with our numbering. If we number from our alkyne, or from the alkyne side first, our alkyne gets a 2. If we number from our alkene, it gets a 1. How do we decide which one comes first, or which one gets the lowest number?
Whatever gives us the lowest.
Whichever one gives you the lowest number. Okay, so you will start your numbering starting with the alkene 1, 2, 3, 4, 5, 6, 7. Okay, so we end up with a 1 ene and a 5 ein. Okay, I don't know why that was worth repeating, but okay.
Sounds fun.
Okay, I can accept sounding fun. So we're looking at that 5 position. You'll notice that I'm not specifying the 2 or the 6. Carbon number 2 and carbon number 6 are part of the pi bond. Why not include them?
Because you always go first, side first.
Only going to number the first one. We don't care about the next one because if we did this correctly, where is the next atom of the pi bond? The very next one. Okay. Otherwise, you did your numbering entirely wrong to begin with. Okay. So when it comes to putting your names together, ene will always go before ein when you compose the name. The numbering is going to go based on whichever one shows up first. And since that's been brought up, we also have an extra substituent out there. We have a methyl group. And that methyl group is located at carbon number 4. So we have 4 methyl, hept 1 ene, 5 ein.
Do we have to?
Sorry, let's get Tim first.
Did you drop the E on purpose?
Yes. So when you're dealing with your functional group, you'll see it with the enes and eins. And as we add in more functional groups, we'll start adjusting those names. So if you go through, actually if we step back, we look at the endings off of some of these. Your actually the ketones are actually pretty high up there. We will go through and drop those the E letters if we add in the other functional groups. Okay. So if we have an ene, ein, and an amine, we'll drop the E's off of both the alkene and the alkyne because the E will show up in our amine at the very end of our name. Okay, so Jerry, yeah.
Hyphen between methyl and hept, or do we just say methyl
Oh,
hept?
shoot, I just deleted it. No, you don't need that space. Go methyl hept. So you'll use,
Methyl hept.
yeah, you'll use the hyphens to separate letters from numbers. The one exception, which we actually should have done already. Good thing I was paying attention. Where should we have been concerned about our exception with our numbering? We needed to specify this name a little bit better. It's not just, what did we say, 4 octane? Whoops, no we don't. Why do we not need the E there?
Oh, because
When do we use E and Z? When you have a double bond. It's the arrangement of the groups attached around the double bond. Okay, so that's why it's not on here. We're looking more at the alkynes, not the alkenes. When we look at the triple bond, where do those groups come out?
straight.
Straight out the side. There is no cis or trans around the double bond. Okay, so it's straight out. So we don't have to worry about an E or Z. You'll notice that I did get kind of mean in the alignment of it because what did I adjust? If we look at where those groups are positioned, it looks like we're looking at those groups being on opposite sides, giving us a trans or an E term. Okay, but realize for the alkyne, there is no E or Z because the groups immediately come straight out. There is no sides of the double bond or the triple bond.
But you would classify the double bond if it was moved over to in between the third and fourth carbon, right?
If we're talking about, I think you're talking about this next one.
The bottom right, yeah.
Yeah. If we shifted that double bond over, absolutely. We'd have to specify our E and Z. Okay.
When is it that you have to use E and Z instead of cis and trans?
When naming, you should use E and Z.
Gotcha.
Stick with E and Z.
Okay.
Oh, cis and
Yeah.
trans,
Cis and trans is
Wait.
kind of a weird gray area. What cis and trans are is I'm looking at two groups and I want to know their arrangement around a particular section. That section can be a ring or it can be a pi bond. Okay, when it comes to E and Z only works around the double bond. Okay, and it's more accurate because that's now referring to the overall structure, not just the arrangement or alignment of two atoms around the double bond. It's referring to everything that's around the double bond. So when you're dealing with nomenclature, stick with the E and Z.
Bottom right, why do you specify NZ after once you move the double bond?
Okay, so let me redraw that one then. Oops.
There's nothing on the right.
If we were going to draw out that structure again,
It'd be just hydrogens instead of carbon, so they'd be the same.
I think that's pretty close.
That's it.
Okay.
Yes.
If we shift that double bond, we would have to go through and specify the double bond being E or Z. And the thing that you're going to have to remember is that you have those implied hydrogens. So in our first step, cut in half, carbon versus hydrogen, carbon's higher priority. Go to the other half, hydrogen versus carbon. Again, carbon's higher priority. Now we cut parallel. Our stars are on opposite sides of that line. Okay, so we would need to specify that they are absolutely on opposite sides, which means the arrangement for this one is with E, not trans, okay, because we're dealing with nomenclature. We want to stick with the EZ nomenclature. It's E because they're on opposite sides. Okay, remember, Z is on the same side. Stop laughing at me. Okay?
Okay, but you said when naming, it doesn't matter. So if they were both like right there,
Yep.
will we go with Alkyne first then, or Alkene? I think I didn't understand that.
Oh, that's going to be an extra tricky one on this. Let's see if I can go back.
I'm assuming we're going to go with the Alkyne because the methyl group, right? It's closer to that?
We clear that back out. Because now when we go through and look at where our bonds are located, we're at a 2 position. And a 2 if we numbered the other direction. 3, 4. Oh, geez, that's ugly. That's really ugly. You definitely won't see that on a test, for sure. That's going to have to be falling back to the IUPAC rule book and try and figure out exactly where that exception falls. You're looking for the primary difference between them, and it would come back to where the substituent is. So what I was really hoping is that our numbering didn't overlap out to the exact same position. And, I would probably, yeah, I'd be guessing. Like I said, I'd be guessing. Right? There is for sure absolutely a rule for it, and it's in a section of a subsection of a subsection. So we've already seen some of those exceptions. If you guys are interested, I'll dig around and see if I can't find the actual rule. Okay? So nomenclature, practice it. You're responsible for it. You'll get directly tested questions on it, and you'll get indirectly tested questions on it, because they'll say, how does this compound react? But they'll give you the name of it. Okay? And you'd be expected to predict what the structure would be, or potentially even what the name of that structure would be. Okay? So you do need to be familiar with the nomenclature, but for the most part, it's fairly straightforward. They aren't trying to trick you. They aren't going to give you these weird exceptions to exceptions to exceptions rules. Okay? So now into the more important part, dealing with the actual alkenes themselves. Okay? So what we start with all functional groups is how can we make them? Okay, so how can we make an alkene? We only have one option. It has to be an elimination reaction. Okay, so to run the elimination reaction, what do we need to start with? So if I draw an alkane here, please tell me how you can get an alkene. Sorry, I'll clean up that mess. We can remove a hydrogen, sure. Where do you want to remove a hydrogen from? Pick a spot. First, second, third. Okay, so if I remove that hydrogen, carbon becomes negatively charged, right? How do I make the pi bond? If we remove hydrogen, carbon is slightly more electronegative than hydrogen. The hydrogen's coming off as H+, which means the carbon has to be negatively charged.
Take another hydrogen that leaves electrons?
Well, before we have.
Take another hydrogen that leaves electrons, so let's take another hydrogen off.
It takes its electrons, sorry.
Okay, and if we did, we're leaving electrons, we get negative next to negative. That's really, really bad. Okay, and the other option, interesting idea, let's have H minus, because then we'd have a positive charge. Is H minus a good thing?
No.
No, that's highly, highly reactive, very, very strong base. Not a good option, so that method didn't work. So what does that mean about the alkane as a starting material? Not good, try again. What we need is something that'll make that carbon positive. So the carbon, to be positive, it needs to be attached to something more electronegative than carbon. Right? Willing to take the electrons, or rather leave with the electrons, and as Teresa keeps insisting I say, a leaving group. Okay? So we need to have some kind of a leaving group attached to our structure. Okay? What leaving group options do we have? We could look at our halogens being our leaving groups, in which case, what do we have? Our starting material would be an alkyl halide. Sorry, I didn't mean to change the pronunciation just because you said it the other way. Okay. Do we have other options for leaving groups? Radicals not going to give you an elimination. Our radicals will do additions and they'll do substitutions. So we could react the radical with an alkane to make the alkyl halide so that we then have the leaving group. Okay. But what I'm fishing for is actually a leaving group, another leaving group. Kind of comes back to the alcohols. We briefly talked about that. Why is OH not a particularly good option? The OH is not a good leaving group, so when we reacted our alcohols, how could we get them to be good leaving groups? We could add a hydrogen, so we react it with an acid first to generate the good leaving group of actually our H2O+. Now that can act as a good leaving group. So that's starting from our alcohols. Okay. Beyond that, we haven't really talked about anything unless you guys can tell me something else. Okay. So what was that?
Probably not.
Okay. So we really just have alkyl halides as our primary functional group. We also have alcohols as a possibility as well. Okay. So we could break that down to the more familiar slide to go through and do or make our alkenes. The mechanism that we'll typically run by will be an elimination, but you will also typically see it as which type of mechanism for your elimination. How many mechanisms do we have for elimination? E1 and E2. Which mechanism are we going to prefer to make an alkene? Why E2? There's no rearrangements. So it doesn't have to do anything with speed. It has to do with the rearrangement option. We don't have that carbocation interfering, so we can go through and guarantee that we get one product. Okay? We just get the elimination. What else is the problem with the E1? Not only do we get rearrangements, but it competes with the SN1. So we'd also lose product yield by going through with an E1 elimination. So we really tend to push E2 eliminations when trying to make our alkenes, okay, at least in the lab. Did I just hit too much? No, I didn't. Okay. The next part of this is doing alkene reactions. Okay, so looking at what we can react our alkenes with. So we can look at alkenes with radicals. We've talked about this one a couple times. I actually shuffled the order around. Yeah, I know. I'm sorry. With the PowerPoint slides, this one was later in the PowerPoint presentation. I brought it forward because we've already talked about it. How do we know we have an initiation step?
There's no radicals and there is radicals?
We start with no radicals and we get radicals. How do we know we have a propagation?
Radicals.
Start and end with radicals, termination. Start and don't have any at the end. Okay? So that would be, come on. Okay? Our formation of a radical, continuation of a radical, or no more radical, in my brief, simple terms. What reagents can we use with our alkenes and radicals? What's that?
Peroxide.
So we do have a peroxide option showing up. We want to be a little bit careful with that. With our peroxides and alkenes, what do we end up with? Okay, this was the part that I was fairly certain that no one really paid attention to. If we just have a peroxide and our alkene, we run a polymer reaction. Okay? Polymer reactions are very, very useful, but if you're trying to do simple small molecule reactions, by definition, that's a bad idea.
So HBr.
Okay, so we want to add another reagent to the peroxide. So we can get our radical initiator in there, our ROR for lack of a better term. We want to add some other reagent, and we can jump in there with our HBr. What happens with this conditions, or these conditions? So it is a homolytic reaction because we're running radicals.
Radical addition.
We're going to run a radical addition reaction, which means the hydrogen and the bromine get added to the double bond. Where did those groups end up going?
Bromine goes to the least substituted position, the hydrogen goes to the most substituted.
Bromine goes to least substituted. Why? Because we generated
Yeah, and that's more
our
stable.
radical intermediate as a secondary radical. That could then pick up our hydrogen to give us our final product. Okay? So we decide where those groups go based on how they reacted. Right? What else could we react with an alkene, particularly under radical conditions? Could go through with NBS. Whoops, shouldn't have done it that low. Okay. Those of you in lab on Monday, what else might we want to tag to this NBS? Light. Those of you in lab today will talk about why we want to tag light with this. What's going to happen with NBS? NBS in light generates a very low concentration of bromine. With a low concentration of bromine, what ends up happening? It's not an elimination. It's a radical substitution where we substitute a hydrogen for the bromine at the allylic position. Why the allylic position?
Because
The intermediate generates the most stable radical. Okay? What happens if we have a lot of bromine? So if we use a lot of NBS and we just get it to generate a bunch of bromine first. Well, and under those conditions, we're going to get a different reaction, which we might see later today. The reason why I don't want to talk about it explicitly right now is it's kind of a mind-blowing reaction. Most people kind of get tripped up with it. Okay? So we'll go through some easier alkene reactions first, and then we'll come back to that bromine one. Is it? Go ahead.
no, is it just the one where we did like the test for unsaturation?
It is the test for unsaturation. It is that exact same.
Gotcha.
Okay. So, addition reactions. I will primarily be talking about alkenes. So, chapter 10, we'll keep coming back to the alkynes every so often. Why will I keep alkynes kind of on the periphery? Not only can they do other stuff, and that's when I'll talk about them primarily, is when they do other stuff, but what are they going to do at the same time as the alkenes? Who's got the right idea? The same thing. Why might they do the same thing? What makes an alkene reactive? The pi bond. Okay. Ultimately, our p orbitals, putting those electron or that electron density further on the outside of the structure. How is our alkyne going to react? With pi bonds. So we're going to get very, very similar chemistry between the alkynes and the alkenes. We did just talk about one thing that was different. Our alkynes have an acidic hydrogen, so we can make them into nucleophiles. We can't really do that with our alkenes. All right? So we're looking at our pi bonds reacting. What do our pi bonds supply? So we're looking at no resonance at this point because we can't see where those pi bonds can shift to. So resonance means it stays within the structure. What our pi bond is going to generate or give us access to are 2 electrons, which means our alkenes and our alkynes will act as Nucleophiles is a good option. What else could they act as? Bronsted-Lowry bases. Okay, and as we talked about at the beginning of the semester, remember when I write bases, I'm referring to Bronsted-Lowry. Okay, so we've got nucleophiles in bases. What are they going to react with then? Positively charged species, which will be electrophiles or what reacts with a base? Acids. So we could write H+, or we could actually even specify acids. Okay. Now that we have an idea on what they can go through and do, we'll want to split through the possible reagents that we could go through under each of these categories. We want to split them because we're going to get slightly different addition reactions depending on those reagents. Okay. What chemistry did you evaluate in general chemistry? Don't tell me general. Acid-base chemistry. Why? The acid-base chemistry was easier to evaluate. Which reaction are we going to look at first? Our acid-base chemistry, because again, that tends to stand out. It's a little bit easier to work with. Okay? Before we actually push into that, I do want to address something here that I like to refer to as bad alkene resonance. Okay? When we look at that structure, we could sort of bring in resonance. Okay? And when most people refer to resonance, they refer to good resonance, which means we don't generate more charge. Okay? If you're going to look for the reactivity of an individual structure, it's really helpful to look at bad resonance. So what do I mean by bad resonance? We want to generate charge, so it's going to make it less stable. So let's take a look at our alkene. How can we do bad resonance with it? So I'll redraw the alkene. Move that pi bond, and more importantly, what in the pi bond?
The electrons.
The electrons. Where are we going to move those electrons?
To the bond between the carbon and the R.
We don't know what that R group is. That R group could potentially not accept electrons, so we don't want to do that.
And onto one of the carbon.
Onto one of the carbon atoms. Well, which carbon?
One with the R group.
We don't know what the is.
How would we find out?
Compare the electronegativity of the R group.
What did we end class with yesterday, Monday? We kept saying a whole bunch. When in doubt,
Pinky up.
I'll have to come up with a better rhyme, I guess. Draw it out. Hey, that actually turned out pretty well. Draw out the results. So if you don't know where to put the electrons, draw both options. See what the result comes out to. So let's look at a red structure to the right. Let's move the pi electrons to that carbon. So we'll look at that resonance structure. We aren't touching the sigma structure, so we can keep everything that has just a standard sigma bond and leave it alone. Okay? So we're taking that pi electron, we remove it from the entire structure, which means what happens to both our carbons? They both become positively charged. Then I'm going to take those electrons and I'm going to put them both back onto one carbon. Okay? If it starts positive and it gains one electron, it becomes neutral. If it gains one more electron, now it's negatively charged. So what we've got is a negatively charged atom out here. What happened to the other carbon? Well, we didn't give its electrons back, so it stays positive. Let's take a look at the blue result of our resonance. What happens in this case? Same deal, we take the electrons out, put them back into the structure, and where are we going to put them back to? Our leftmost carbon. So it'll become negatively charged, and what happens to our rightmost carbon? Positively charged. Both of these structures are charged. Are they both equal? Don't think so. Good answer. So which have we talked about the most? The positive charge and the negative charge? Positive charge, carbocation stability. Good answer. Where's the carbocation most stable? On a tertiary position as opposed to a primary position. Which one of our resonance structures puts the positive charge in that position? The red one. Okay? Well, we've got two charges, so we should evaluate both. Okay? And we kind of glossed over, talked about it a little bit, but kind of left it hanging. Negative charge. Where's the negative charge most stable?
At the
The least substituted position. Which structure puts the negative charge on the least substituted position?
red one.
Red. What does that mean?
Red one at best.
If we are going to be concerned about the reactivity of an alkene, what we're looking at is the bad resonance, where we put the negative charge on our least substituted position and our positive charge on the most substituted. How does that help us out? I now know a positive and I know a negative attached to one atom in both cases. If I now react this structure with, say, an acid supplies what?
H plus.
H plus. Where's that positive going to go?
To the right.
To the negative hydrogen.
Negative
Right.
carbon.
Carbon. Good call. Negative carbon. So our red structure. We then have that carbocation. So what else would we be looking for in the solution to stabilize that positive charge? A negative, also known as a
Base.
Lewis base, also known as a nucleophile. Okay, why not a Bronsted-Lowry base? It's reacting with hydrogen. Our positive charge is on a carbon. Okay, so those definitions are important because if we can identify some balances of charge, we can start to then predict what they're going to react with and then apply that pattern to everything. Okay? So, within our mechanisms of addition, so now we're going to take it a step further. We're going to take our reagent now, X and Y. Okay? What charge is X? Can't tell, why not?
Made up.
What partial charge is it? Way to find the loophole on the neutral.
Made up.
How would you find out if it was positive or negative? If I went through and said that X was a hydrogen, what partial charge would it be? Y is a hydrogen. Ah, how do you know it's neutral now and not positive?
Why would they not be XX?
How do we know the hydrogen is positive in this case?
Because it has higher electronegativity.
The difference in electronegativity. I can't repeat it enough. Look at your electronegativities. Okay, what is the definition of electronegativity? I know this is going to hurt everybody. Difference or definition of electronegativity.
The more electronegative, the more
Not
we
quite.
hold on to attraction for bonding electrons.
The more electronegative, she knows because I've been yelling at her about it. The more electronegative an atom is, the more likely it will steal or hold on to bonding electrons. Not general electrons, bonding electrons. Why is that important? What's connecting the hydrogen to the oxygen? A bond. If oxygen is more electronegative than the hydrogen, what are those electrons doing? Spending most of their time on the oxygen. So what we just came up with and did is actually said almost a resonance effect. Let's push that to the extreme. Oxygen straight up takes those electrons. What would our horrible, horrible, horrible resonance structure be in this case? Hydrogen would be
Plus.
positive, and our oxygen would be
Minus.
negative. What does that do? That tells us our hydrogen in our original structure is what partial charge?
Positive.
Positive, our oxygen is negative. Why is that important? If I know the charges, I can now match the charges up in the other structure. Okay? So go back to your differences in electronegativity to predict. Okay? In this case, I removed those. Why? Because I don't want to decide where those atoms are necessarily going. All I want to do is decide where they can go. Okay? Back to the pi bond structure. So let's say our atoms are going to share electrons with our pi bond, or our pi bond is going to share electrons the other way. Where are there electrons in the pi bond? Good, pi bond. In the p orbitals, where are the p orbitals? Above and below. Which means every time we react an alkene, it can react both above the plane and below the plane. Which means we're going to end up with a stereochemistry issue. We'll always get two products. Okay? The relationship between those two products is another issue. If those two products are the same, then we end up with one product. But if they're not the same, then we've got enantiomers or diastereomers, whatever else could potentially come out of that. Okay? So you have to realize, as soon as we do an addition reaction, we immediately run into the issue of two possible products. Okay? And that has to do with the dynamics of the p orbitals. Okay? So let's make our first assumption. Let's say xy interacts with these p orbitals. Where would I expect xy to be? Let's say the top of the p orbitals interact. Where would I put x and y? I know it's kind of a weird question.
Do we know the electronegativity?
No, we don't know electronegativities. All we're doing is saying we're just going to make the connections.
Say it again.
Okay, we could put x here, we could put y here, right?
Oh,
And we could then delete the bond in between,
yes.
right?
Well, they would go opposite each other.
Is there another way we could do it?
One above, one below.
We could put the x up top and we could connect the y, sorry for this one, from the bottom. That's just a really long bond. Okay, so let's take a look at what that would look at in a slightly different version. In our top case, what happened? The x came in from the top and the y came in from the bottom. How could that possibly happen? What has to happen to the x bond y? It has to completely break, okay, and go off free-floating in solution. Why? Can I possibly get the x to attack the white lobe on top of the structure and the y to attack the gray lobe at the bottom of the structure? Okay, that can't possibly happen at the same time, so we have to cleave that bond open. What about the bottom situation?
They can do both at the side.
They both connected to the top. Are these products potentially different?
Yes.
Yeah. So what we're going to look at now is the dynamics of our addition reactions and what could potentially come out of these. Okay? That top circumstance is what's known as an anti-addition. Why would we call it an anti-addition?
Because the X and Y are in the anti-position.
If we rotate that structure and look at it from a Newman projection, where are the x and y? Anti-conformations to each other. We look at the other one. Any guesses on what the name might be for the bottom one?
Yeah.
Are they Gauss in this case?
Oh, they know.
Technically, they're eclipsed. So yeah, it's almost that. It's a sin addition. I was kidding about the almost that. Eclipsed and sin don't sound anything like each other.
They both have an S.
They do both have an S. Whatever works for you. Okay. Is there another option?
You did both.
Gap.
No preference. In the course of the reaction, we have no preference over sin or anti. So we could end up with a mixture. Okay? So we do have these three possible options coming out of this. So we can call that 2, 1. Give me a second just to write that out. And a third, no preference.
Can't the sin one just rotate to make?
It can rotate to get the Y into the anti-position, but then what happens to the R groups?
Oh, those move in different.
Those are going to move into different positions and you'll have different products. Okay? So that's a really important distinction to realize. So what he's talking about is if we take a look at that sin product and we rotate about that sigma bond, you're right, you can absolutely set it up so that X and Y appear to be anti to each other. But where are the other groups? We've got R prime and R double prime. As we go through and do that rotation, for our sin, which way did I decide to rotate this? R prime would be up. Did I do that right? And it's a good thing I numbered it correctly on the other side. It looks like I changed the numbering.
No, that's backwards.
The backwards, yeah, there you go.
Okay. So they end up not overlapping. So we get different products coming out of this. How did we discover that we had these two different types of addition reactions? This is the other fun part about this. Huh? True, that's how they came back to this. Someone went into the lab and tested it. Said, I think we only comes in from the top. I think we only get this sin addition. We never get this anti-arrangement. So I'm going to go into the lab and test it. Whoops, I'm wrong. What do I have to do? Fix my theory and try again. Okay? Or I go into the lab, I get it right, I publish, and everybody thinks I'm the great and most amazing person on the planet until somebody else says, I don't like him. I'm going to go into the lab and design an experiment that proves he's wrong. Okay? And we end up with both those possible options. Okay? So what you are learning in organic chemistry is not someone that sat down at a desk and said, okay, yep, sin addition. Boom, there's the answer, I'm done. It's, oh, I think it's a sin addition. I'm going to go to the lab, Here's 20 hours later, look at my results. Oh, crap, I'm wrong. Okay? And yes, if you haven't heard that already, science is failure. Okay? The fun part about science is when you fail, you get back up and you do it again. Okay? And then it kicks you in the shins and you fall back over. Okay? And you get back up again and do it again. Okay? Talk to some of the more famous scientists. What they talk about is not all the failures. They talk about that one time it succeeded, because that one time they exceeded, they're adrenaline junkies. It's absolutely amazing. It's the most coolest thing on the planet. I win! Until someone comes along and kicks you in the shins again. But at that one instant where you think you've got everything down and ready to go, it's a phenomenal feeling. And that's what scientists strive for, okay? To get beyond that failure. So, nice slide to follow with. What do we have on this? I like to refer to this as a spider diagram because it's branching out from a central start point. Our starting point in the middle there is an alkene. It's a very particular alkene because it's asymmetric and it also involves a ring. Okay? The reason why is I can get a cis and trans alignment around that ring. I can look at the pieces that I add, my X and Y, and I can look to see how they are aligned. The ring helps because, as Jerry was suggesting, when we go through and do that rotation, it looks like we get the same product. With a ring, can you do that rotation? No. No. So you're locked in that permanent position. It allows you to see the results much cleaner. All right? So with this ring structure, what we've got is a whole bunch of spidering outwards of reactions. We've already talked about sort of some of these, and we're going to go into some details on them. Okay? How I would break it up. We've got one section right there. What's special about that one section? What do you see as far as the reagents go? They're all acids. So we'll look at our alkenes acting as bases. The other section, this is where it gets dicey. We could really go through here. What's special about that one? That's our radical addition reactions. Okay. After that, now is where it gets kind of troublesome. We could kind of group that whole last section as our alkenes acting as nucleophiles. I've got it subcategorized into the slides as what I would call, and I'm sure you'll love this, obvious. Did I spell obvious right? Obvious.
Yeah, it looks like there's
Obvious electrophiles. Keep talking. Obvious electrophiles and our non-obvious. Okay? When I say obvious, I'm not saying like, oh, you don't know that. I'm just saying it's a little bit easier to see where the electrophile is. Okay? So we've already talked about the radicals. Where we'll focus today is definitely the acids. I think the acids will be very straightforward. Hopefully you guys will be able to pick those up fairly quickly. Okay? Then obvious electrophiles is where I would like to get to today. Cover that, and then we'll move into our non-obvious. Some of you have seen the non-obvious in lab. We'll talk about that on Monday, and then we'll move into a whole nother set of alkene reactions, the oxidation and reduction reactions, one of which is on here. What's that last one that I didn't circle? What happened in that reaction? Added hydrogens. What's our definition for redox? Could look at the exchange of electrons. Right. Depends how you're taught it too. If we increase the number of hydrogen bonds, let's try it the other way. If we oxidize a structure, we increase the number of, what does oxidation sound like? Oxygen. If we do an oxidation reaction, we increase the number of oxygen bonds. If we do a reduction, what are we going to do? Decrease the number of oxygen bonds. We don't see any oxygens in here. What's the other option? We can increase the number of hydrogen bonds for a reduction. So that orange one is a reduction reaction. Okay? So that's chapter 12. Okay, questions? Yeah, you can shake it off. That's fine. I understand that. Okay? There are some other names that are going to float into this. I'm really bad with names, and I get them backwards all the time. I will try to introduce these. If not, read your textbook. just because I'd rather you understand the chemistry than understand the name associated with it. Okay? Yeah, it's Markovnikov. Why do I not like this? We have Zaitsev already. We have Hoffman. We've got Markovnikov. There's anti-Markovnikov. There's another name, I'm sure, in there that I'm forgetting. Okay? Everybody that discovered a reaction got to attach their name to it. Good job for you. Way to make it difficult for everybody else to figure out what's going on with the chemistry.
How come
Okay.
science didn't discover reactions?
How about what? Who? Sorry?
Someone
Smith?
with like one syllable easy pronunciation names
Oh,
people.
yeah. They're usually Russian. They have nothing else to do during the winters. Sorry, that was recorded. Never mind. Alkenes is bases. So what we're looking at is our 3 primary reactions. Quickly, move on. We've got 3 primary different reactions. Okay? All 3 of those, I'm accenting the fact that we have H+. Okay? In the very first reaction, you typically won't see it written out as H+. And I know it's up off the projector there. But you will probably see that first reaction written out as, say, HCl, or HBr, or HI. Why? Those are all strong acids, which in theory, hopefully at this point, you remember, will completely dissociate into the ions H+ and that halide ion. Okay? So when we go through and look at these, what we should be evaluating is the most reactive thing in all 3 of these cases. Okay? And this, we're starting to get more and more into the face test. Okay? Which of these things would you least want splashed in your face? Okay? Any of those H contained things, okay? Because all of those are acids that are supplying what? H+. Which means what do we need to find in our other material? A negative. We need to find something as negative as possible to react. Okay? As we continue to add more reactions in, you're not going to be responsible for running one reaction. You're going to be responsible for looking at a reagent and a substrate and have to decide what of 6 possible reactions can occur. Okay? And you have to find the best one. How do you decide the best one? Well, it's going to be the most reactive positive with the most reactive negative. As long as you can identify those positives and negatives, you should be set to go through and start at least guessing your way through a problem. Okay? It's an educated guess, so don't give me too much crap on saying it's a guess. But it is educated, and you can actually start to predict on something you've never, ever seen. Okay? So, we said the acid was bad. What do we need to find? A negative. Okay, so we've got H+. What is that H+ going to react with? Where's our negative? The pi bond. So let's take electrons from our pi bond and let's share them with the H+. How do we show that? We'll start an arrow at our pi bond and share them with the H+. What's the result? Where does that H+ go? Because that pi bond has electrons that are coming from 2 carbons. Which carbon is the one that actually forms the bond with that hydrogen? What if you don't know? How many people don't know where it should go? Guess what you should do? Draw it. Draw both possible answers and see what happens. Okay, so let's draw it. Try and maintain the same patterns. Let's put the hydrogen there in one case. And in the other case, let's put the hydrogen on the other carbon. Both of these have showed the hydrogen reacting. I like your skeptical face back there, Isaac. What's wrong with these 2 structures? Okay. Can accept that. We haven't shown the positive charge. We took the 2 electrons from that pi bond, we took them out of the structure, which meant both carbons became positive, and we put them back into the structure associated with only one of those carbons. Okay, so the other carbon had to become positive. In our top structure, where's our positive charge? Our primary carbon on the left, does it really matter? In this case, why not? It's identical in both cases, actually. So any way I draw it, it's not going to matter. Okay? Make sure that when you have a more complicated problem that you are identifying your positive charge to the atom that was part of the pi bond. How about in the bottom case? It's our secondary. What's the difference in energy between these two? Is one more or less stable than the other? Yes. The secondary is a better carbocation than the first one, which means which product or which intermediate actually forms? The bottom one. So by understanding something about the stability of where our charges are, we can actually start to predict what's happening with our reaction. Is that positive charge stable?
No.
No. It's really unstable. What do we want to stabilize that positive charge?
Electrons
Where could we get electrons?
from whatever took it from the hydrogen.
We need to find, and I like the best wording on this, a nucleophile. It doesn't have to be the atom that took the electrons away from the hydrogen. In the case that we're starting with, I decided to stick with our first reactions. We were looking at probably, let's just say HCl. Which means once we react the H+, what's also floating around in solution? Cl minus. Well, I have a negative and positive. What should I do? Put them together. Show my curved arrow with the chloride attacking the positive charge. What's the result? And that's typically how it gets written, given that's a Cl. Okay. I heard about what? What's the but what? Okay. What if I went through and did this? Does that make it more obvious? Yes. Okay, I intentionally left that hydrogen off because that tends to trip people up. Why can we get rid of that hydrogen? It's an implied hydrogen. So when you look at a multiple choice test, the answers they're going to give you aren't going to show that hydrogen. Okay? You have to be aware that it is present. All right? Everybody see that? Okay. Fun question with this. Let's make it HBr. What happens? Good answer. I like that. Same thing. We put on a chloride, right?
No, the BR is the substituted position.
I was just kidding. Maybe we want to change that up. Where does the Br go? Still absolutely goes
When we did the
here.
radical one that I did that.
When we do a radical addition, where did the bromine go? The least substituted. So you have to be very careful with what reagents you're using, because that's going to determine which mechanism you're running on. Okay? How do we know we're not doing a radical reaction in this case?
Because there's no
We don't
light
have any.
and or R.
So light is a possibility, but when we're doing the radical additions, we typically don't add light. We have the peroxy species. So if we were going to run a radical addition, we're looking at our peroxy species, and they typically just leave it as a peroxy, but almost always you'll have heat kind of implied with it. Okay? That's how you know you're running a radical. And the biggest difference with this is that the radical reaction put the bromine on the least substituted position. Okay? So that's a really massive distinction between these two mechanisms. How do we know where the bromine was supposed to go? I'll accept 2 answers on this. Maybe 3, depending on how creative you are.
Because it's not a radical.
It's dependent on the mechanism. So you understand the mechanism to determine where the pieces go. And the most important part of the mechanism to decide where everything went was looking at the intermediates that were generated and making sure that you establish the most stable intermediate. Okay? Other option. This is why most people don't like organic chemistry, because they don't like or don't see that it's a question of understanding how the atoms move, or they aren't taught it. You memorize. Radical addition, what happens? Bromine goes on the least substituted. How? I don't know. It just goes there. Okay? You get both options. Okay? I highly recommend that you understand how it works, because you can apply the how to everything. If you just memorize it, it will make it a lot more challenging, particularly when we triple the amount of reagents that you have to know. So understand the how. So next question, or let's step back. Any questions that you guys have?
I have a question.
Yes.
When we added the H plus, did we use one of the examples up there, or did we just say H?
We were using those examples as a starting point for this. And in all those cases, what did we have?
Yeah, the H.
We had H plus. Okay, so with all of those cases, we have H plus. That's how we can push this reaction, which is actually going to get to the next question that I'm going to ask. Let's not use a halogen. I don't want to use bromine anymore. I don't want to use chlorine. What I'm going to use instead, pen, not pen, it just wasn't working. I'm going to use water. What's our nucleophile now?
The OH, right?
Be a little bit careful. Can't say OH minus. What is OH minus?
Oh, it's water.
A strong base. How did we start the reaction? With an acid. If we add an acid and a strong base, we get the acid-base reaction, which neutralizes it, nothing happens. Okay? So it's not a strong base. It's a weak nucleophile. And here's why it's really important to realize that your heteroatoms have lone pairs. Why is it important to recognize that they have lone pairs? We just found a source of electrons. We just found a nucleophile. Okay? Again, when you're looking at your exams and probably the homework questions, they'll draw it exactly as I drew it first. How many lone pairs are on that oxygen? There are 2 lone pairs. I didn't draw them. That doesn't mean they aren't there. Okay? They become implied. If you remember that they're implied, when you look at the next step, what happens is our oxygen can act as a nucleophile, and our product becomes ish. Positive charge on the oxygen. Have we reached a stable product? No. What happens? The oxygen will take the electrons away from our hydrogen, and now we end up with our final product with the OH. And we'd have H plus floating off on its own.
Is it more stable to have H plus on its own, or to have the secondary carbocation?
More stable for the H plus. Okay. Another fun question that you'll see pop up every so often. What took the H?
What do you mean?
The water.
So in our mechanism, and I'm going to have to get up and probably point at it. I just erased the arrow. We had the electrons from our hydrogen going to the oxygen. That means we just drew H plus floating off on its own. You'll find a lot of people aren't happy with that. Okay? You have to have something take it. Okay, well, what's got to take it? Something with electrons has to take it. What's that something? Anything with electrons has to take it. What's the most likely thing in this reaction? The water. Okay, so water would be the most likely thing to pull that off. Okay. How do we know that? It's a concentration issue. One of the reasons why I don't get very nitpicky with it is that, do I end up with the same product? Yeah. Do I end up with the same overall mechanism, except missing one extra little tiny step? That's the only thing I'm missing. Okay? And what we're doing in that case is an acid-base reaction. How easy are acid-base reactions? How fast are they? Okay? Super fast, super easy. Why do I care to spend my time writing it out? Okay? So if you're somebody that absolutely wants to show that on there, or if you take a future class where they absolutely insist on you showing something, take that off. If you have no time, this is my favorite answer. What is B? B stands for base. But if there's a base, how do I get away from the acid? Is it a strong base? How do you know it's a weak base? It's not negatively charged. Okay? So we can dodge that bullet very, very quickly, sidestepping and just saying something basic comes in and takes it off. I don't care what that something is, but I know it has to have electrons, so there's a lone pair to take it off. Okay? Depending on the reactions, you may see more specifics or less specifics about what atom is pulling that off. It becomes much more prevalent in second semester, then it just turns into a nightmare, because every reaction that you go through and do has probably 6 acid-base reactions that run with it. Okay? So kind of be aware of those kind of steps within this. Questions about our alkenes as bases? Ready for a new problem?
Sure.
Here's a new problem. What's our answer?
Oh, it just attaches the same.
I'm liking what I'm hearing. Same thing, yeah? Just go through and erase one of those hydrogens and turn it into a CH3.
And then it eventually becomes the steric hydrogens, right? Longer chain.
We can address that in a second. Oh my gosh, whole new reagent, whole new system we have to worry about. Exact same thing. Nothing changed. Okay, let's be more obnoxious. Because you like it when I'm obnoxious, right? Here we go. Dun, dun, dun. I think I drew too many carbons. What's your answer now? Yeah, I know I can't count. Stop counting. That's 6 carbons. I promise. Okay. And what Diego brought up was an interesting question. Okay. That oxygen has to act as a nucleophile. What happens is I start to add more and more things to that oxygen. Let's say if I jumped it up to something along these lines. Let's get crazy with it.
It's pulling more electrons, right?
No, what was your question? What was your statement, Diego?
Oh,
It becomes more sterically hindered, which does what to the nucleophilicity? It makes it less nucleophilic and less likely to do the reaction. So when you're thinking about synthesis reactions, if we look at a final product, we want to be able to decide which of those bonds in our final product is going to be the easiest to make. And if steric hindrance is going to come into play, I'm going to want to move to the least sterically hindered bond to go through and make, because that one's going to have an easier time of that reaction. Okay? When we push into synthesis after we put all this together, we'll come back to that issue about deciding on how to make an individual structure. Okay. Any questions about our alkenes as bases? Look at that, one slide, and we did like 6 examples and a bunch of squiggly lines. The reaction rate drops drastically. We will probably not get a good yield with that last species. Okay. We would still expect the same result. Okay, our same result is still a bunch of squiggly lines. Okay. But our yield would be much, much lower because we now have a steric hindrance preventing the nucleophile from acting as a nucleophile. If it can't physically act as a nucleophile, the reaction can't go forwards.
Can we provide heat? Does it help? Does it help?
Does what help?
Heat?
We can add heat. We can do all sorts of other things to help facilitate that reaction. Yeah. Give it heat and lots of time. 3 minutes, right? I can do all of this one in 3 minutes. I'm just kidding. I am, I promise. But I do want to kind of talk about these 2 reagents. These are the obvious electrophiles. Okay, what is the obvious electrophile for that first row? Actually, let's take a step back away from that. You'll notice that we have a slightly different situation here. What we've got is 2 reagents or 2 steps. So to go through and use either the BH3 or that mercury compound, we have to do the reaction in 2 steps, which means 2 sets of reagents. This doesn't mean 2 mechanistic steps. Remember with that last slide that we looked at, we went through and did 2 to 3 mechanistic steps? That was with 1 reagent. That was 1 reaction step with 3 mechanism steps. In this case, what we're looking at is 2 reaction steps. Each of those reactions is going to have their own independent mechanism associated with them. Okay? Why are we doing this? What we're going to go through and do in the process of each of these conditions is react the alkene with our electrophile to generate a stable intermediate. That stable, or not stable intermediate, a stable product. That product is reactive enough that I can put it under some more conditions to push it to something that I actually want. Right? And in the case of both of these, what we're putting on ultimately is an oxygen and a hydrogen. We're adding OH, or we're adding water across the double bond. Right? Where the OH goes, and if it's necessarily actually OH, is going to be dependent on the reaction mechanisms for each of these. So before we leave, what I'd like to address is what is the electrophile with both of these. Hopefully the boron one's a little bit easier. So our electrophile is going to be in the first step of both reactions. And I'll give you a hint. In the first one, it's BH3 is our electrophile. And the second one, it's our mercury, OAC2. We'll address that. Let's look at the first one first. What's special about BH3? What's its Lewis structure? You all remember how to draw Lewis structures, right? 3 bonds, BH3. Does it have its octet?
No.
No. So what do we do?
Put a lone pair, but it doesn't need that.
So what I'm fishing for is you go, oh, we always need an octet, and we put a lone pair in. You cannot do that. Remember what we talked about at the beginning of the semester. You must count in total the valence electrons that you put into the structure. How many valence electrons does boron bring in? 3. Electrons from hydrogen? 1 each. We've got 3. 6 total electrons need to go into this structure. Once we've got in our sigma bonds, what's the problem? We're done. We cannot put a lone pair in there. What's the hybridization of that boron? What's left over? We have a p orbital. How many electrons are in that p orbital? None. How many electrons can we put into a p orbital? Where are those 2 electrons going to come from? From the alkene. Our pi bonds from our alkene. Our boron is the electrophile. Right? That's going to change how our reaction works. We'll pick up there on Monday. Okay? The mercury, as you're packing up, OAC, which comes back to another issue. I could also draw out the alkene like this. What does Me mean? Methyl. Right? Just like we had ethyl, and I did ET. Me is methyl, meaning we have CH3. What is OAC? It's an oxygen bound to AC. Sorry, I had to. The AC that's an acetyl group. Okay. Why might that contribute to the reactivity of our magnesium? Or mercury, thank you. What's the charge on oxygen? Negative. If we have 2 negatives attached to that mercury, what charge is the mercury? Positive charge. There's our electrophile. Okay? Sorry, I'm done.